Welcome everyone to another session. The next speaker is Professor Eknath Ghate. He will speak on modularity and Galois presentations, modularity, modular forms, and elliptic curves.
Okay, so thank you. As you know, my lectures are very elementary, and I'm continuing at that same level for at least the first 3 lectures. And yeah, maybe at the end I'll make some more advanced remarks, last 10 seconds, literally. But this is an elementary lecture. So actually, first lecture I should have said was essentially from chapter 1 of Diamond-Sherman. And this lecture is from chapter 5 of Diamond-Sherman, in case any of you are looking. I'm skipping 2, 3, and 4, but I'll give a quick overview of those in the 3rd lecture. Okay, I think lecture 5 is important because it has heck operators. So what we're going to do today is define heck operators, both on modular forms and on modular curves. And at the end, I'll explain a moduli interpretation of the heck operator, because, you know, modular curves are moduli spaces for elliptic curves with some level structure. So we want to understand what the moduli interpretation is of the heck operator. Okay, so we'll write some formulas down at the end. All right, so start. So one starts a little abstractly. If you haven't seen heck operators before, this may look very strange, because usually it's just the formula given to you. And that's more or less the case in Diamond-Im, which I don't want to follow therefore. Because just seeing a formula straight away without any motivation is maybe not so good. So, but of course, Diamond-Sherman expands on that. So let's follow that. So double coset operators. So we need a few lemmas. Even if you've seen heck operators before, this sort of discussion in Diamond-Sherman is very nice. He sort of motivates why you have these very explicit coset representatives, which is not there in most books. So let's do this. So suppose gamma is a congruent subgroup. So congruent subgroup I didn't define, but it just means that the subgroup of SL2Z, which contains some gamma n, principal congruent subgroup of level n, I defined last time, for some capital N. In particular, it has finite index. So, but you don't need gamma to be gamma 1n or gamma not n or something specific for much of the discussion. So some level of abstraction. But if you're confused, think of gamma as gamma 1n. Then this group is also a congruent subgroup. So here, this is for all alpha belonging to GL2 plus Q. So alpha is a matrix with rational entries, and the determinant is a positive number. For many of these things, probably you don't even need that, but for applications, suffices to take determinant positive. The main matrix here will be 100P or something like that. Spoiler alert. It's all going to boil down to alpha being 100P, diagonal matrix 100P, but you can develop the theory for general alpha. Okay, so simple statement. So, okay, proof. I'll do some proofs today, more proofs than last time. So since gamma is a congruent subgroup, we know that there's some n bar we want to show this is a congruent subgroup. We want to show some gamma n is sitting in here. The obvious one doesn't work. The one that works for gamma doesn't work. So let's start with n bar for gamma. We know this. And let's assume that n bar is so large such that the following things happen. So n bar, when you multiply it on alpha, n bar is just a number. Alpha is a matrix. When you multiply all the entries of alpha by n bar, alpha has some denominators. but you clear denominators. This is actually an integer matrix. The determinant now, and it may not be in GL2Z, of course. GL2Z determinants are just plus minus 1, so that's impossible to happen most of the time. But you can assume this, and let's also do the same thing for the inverse. So just clear denominators. Okay. And now you set n to be n bar cubed. This will work. Okay, so small computation. Let's compute alpha gamma n alpha inverse. What is this? So this is 1, my definition of n. It's 1 plus n bar cubed m2z alpha. We take alpha inverse over here. Right, and now let's write this as just 1. This alpha with alpha inverse just gives you 1 here. And let's distribute the n bars nicely. Let's distribute them in the following way. Let's write this as n bar alpha plus m2z n bar alpha inverse. I think I've written all the things, not plus. Yeah. Right, so small, just a distribution. And now here, this is an M2Z. This was obviously an M2Z. And this is an M2Z. So putting all this together, we see that this is in gamma n bar. Okay, so therefore, gamma n sits in alpha inverse gamma n bar alpha. And of course, gamma n sits in gamma by choice. It sits here. This works. We managed to put a gamma n inside this group. So this is a congruent subgroup. So this is the first remark. Okay, the second lemma is maybe a bit more interesting. Okay, so suppose that you have two congruent subgroups. And let gamma 3 be the following intersection that came up in the previous lemma. Alpha inverse gamma 1 alpha, slightly different. Gamma 2, a bit more general maybe. For alpha belonging to GL2 plus Q. Then we have the following bijection of cosets. So in Heck operator theory, there's this double coset and we have to break it up into single cosets. It's a little tricky how to get representatives. So this lemma helps us do that. So here we have this double coset and we go modulo gamma 1. The claim is there's a bijection between that coset space and that coset space. Okay, maybe the statement of the bijection, the map in the bijection, I should also write down. So here, let's write this as gamma 3, gamma 2j for some j. So there's no claim about the finiteness of either of these things. There's just a bijection between cosets. And these are in these representatives are in bijection with gamma 1. So we're multiplying on the left by gamma j. Multiply on left. I mean, this is just in quotes. Multiply the representatives on the left by alpha. Okay. All right. So this is we worked out the proof. So there's a map from gamma 2 to gamma 1 alpha gamma 2 mod gamma 1, this coset space. We'll just take gamma 2 to this coset. Gamma 1 alpha gamma 2. Okay, so let's just look at this map. This map is clearly a surjection because every coset representative is of this form, so you just choose the appropriate gamma 2. There exists a surjection like this. So that's good. And what's the kernel? Well, the kernel is more or less by definition gamma 3. So let's just work that out. We're over gamma 1 alpha gamma 2 is equal to gamma 1 alpha gamma 2 prime. So maybe I won't write the whole proof. Just check this. Gamma 2 prime, it's more or less obvious mental exercise. I won't write all the 5 steps. Gamma 1 alpha intersection gamma 2. I just put, instead of putting a capital gamma 1 here, just put some little gamma 1 and little gamma 1 prime, and then work things out. Work out that inverse, and you'll see that you're in that space. Okay, so good. So this is surjection, and this is the kernel of this map. These are not groups, quotient groups or anything like that, just coset space maps. So, okay, therefore we're done. Okay, corollary of this is that this group, gamma 1 alpha gamma 2, is a finite, the number of cosets here is finite. This double coset space, if you break it up into single coset, then there are finitely many representatives. Okay, so what's the proof? So by lemma 2, we're trying to show this set is finite. It's enough to show that this set is finite. Enough to show that that's finite. Right, but this now is obvious. But gamma 2 is sitting in SL2Z. So gamma 2 mod gamma 3 is sitting in SL2 mod Z mod gamma 3. And gamma 3 by lemma 1 was a congruent subgroup. I mean, okay, not gamma 3 exactly. I think I need here alpha gamma 1 alpha intersected SL2Z. Sorry. So we have an inclusion on the numerators, you get this inclusion on the denominators, and this is a congruent subgroup, so this is finite index. Okay, so we have that this slightly strange looking object, breaking this double coset into single cosets, can be done in a finite way with finitely many representatives. Right? So now let me start to apply this to modular forms. So for that, let's recall the following definition. Not really a recall because I didn't define it in this generality before, but just in some weaker form. But there's this slashing action which shows up all the time in the theory of modular forms. If you have some matrix beta in GL2Q plus, then you define function on the upper half plane belongs to H. F is the function on the upper half plane to the complex numbers. F slash beta at tau is a new function. And what function is it? This time your matrix may not have determinant 1. It's not in SL2Z. The determinant is in GL2 plus Q. So you need to choose this term very carefully and intelligently. It turns out to be this power of determinant. And then the other stuff is just the usual action. d tau plus d to the minus k f of beta tau. All beta, all tau. Okay, so that's the slashing action, and the definition of the double coset operator will be written in terms of this slashing action. Definition. Let's fix. I'm going to use some notation without writing it every time. Gamma 1 and gamma 2 are congruent subgroups. So for F, a modular form, I guess I formally didn't define this, but I defined it for gamma 1n or gamma naught n, but same definition for any gamma. That F slash gamma 1 alpha gamma 2 of tau to be equal to the sum F slash beta j of tau, where gamma 1 alpha gamma 2 is equal to, you know, there's a finite union here, just pick some representatives, gamma 1 beta j. There's a finite disjoint union. Okay, so I thought I'd spend some time on the lemmas before writing this and just saying that the union was finite. So most people don't check that. But why is this well defined? Why is this some finite? You don't want to add up infinitely many things. So that follows from these two lemmas. You're doing a finite sum. So this is a definition. And you can see it really doesn't depend on coset representatives. Why is that? If you place beta j's on the left by things in gamma 1, and then those gamma 1s get swallowed up, right? So it's independent of the coset representative beta j that you choose. These two things can differ by some gamma 1, little gamma 1 on the left. But that doesn't matter because the slashing action sucks them up. So, well defined. Right? Okay, so now let's check that the slashing action actually takes modular forms for gamma 1 to modular forms for gamma 2. So claim. Slash double coset operator actually takes modular forms of weight k and level gamma 1 to modular forms of weight k and level gamma 2. You can think of gamma 1 equals gamma 2 equals gamma 1n. This is sounding confusing. Okay, so this is just a generality. The proof. So it boils down to the following observation, that multiplication on the right by an element of gamma 2 induces a bijection on the coset space. These two sets are in bijection. We know they're so what I'm trying to say is that the multiplication on the right permutes the cosets. Okay, so it may not look like it because your beta j's, there's no beta j's here, maybe it's just beta here for any beta. So these things get permuted around in this way, multiplication by gamma 2. One of the beta j's will go to another beta j. So maybe I won't check this. I try to check all these small things by myself, but okay, so we'll use this principle. Okay. So in other words, putting this, saying this in another way, if gamma 1 beta j are disjoint cosets, with union gamma 1 alpha gamma 2, then so are the gamma 1 beta gamma 2. Also disjoint union. Disjoint cosets with union gamma 1 alpha gamma 2. Okay, so beta j gamma 2 is a new set of coset representatives. Now we're done because just take the definition now. So what do we have to check? We have to check that this is a modular form. We have to check that when you do the slash, you get a modular form for gamma 2. In fancier language, that's just checking that when you slash by gamma 2, you wind up with this function again, right? You just have to check that. So a small computation. So this is joint union by the definition over there. F slash beta j slash gamma, which is F slash beta j gamma. So this is also gamma 2. This is also a bunch of coset representatives. So by definition, this is just okay. So as far as the automorphy property is concerned, we're okay. This function after you slash by gamma 1 alpha gamma 2 really is invariant under slashing by capital gamma 2. So at least it takes, it preserves the automorphy property on the left, goes to the automorphy property on the right. And what about the cuspal condition? Holomorphicity at the cusps, vanishing at the cusps. Say the same thing for SK gamma 1. So that's almost by definition because, for example, if gamma 1 and gamma 2 are gamma 1n, to check holomorphicity of, remember all these functions had to be holomorphic at infinity, right? For every alpha, I said this yesterday. So holomorphicity at the cusp is also preserved. So there's a finite sum of holomorphic functions at infinity, finite sum of sums vanishing at infinity, etc. Check holomorphicity at cusps. Okay, so, and similarly, if you want to go from SK gamma 1 to SK gamma 2, you have to check that the vanishing also, the finite sum of things that vanish at the cusp, so has to vanish. So, okay, so this is the definition maybe that people have seen in some time in their life. There's another one on the modular curve, which is very interesting. So I want to do that also. So basically, these double coset operators, they eventually will become Heck operators. The Heck algebra acts on everything in sight. A good sort of slogan to remember. You see some weird object, looks like it's built out of modular curves or things like that, bound to have some Heck action. Jacobians, cohomology, group cohomology, modular forms, modular curves, everything inside there's usually a Heck action. This subject. So let's do one or two of them today. I'm doing just on the modular form one. Let's do the modular curve one. At some point I'll do the Jacobian one, etc. The only one I won't do is the one acting on parabolic group cohomology, which is needed in the proof of the Eichler-Shimura isomorphism. I'll mention that at the end. Very similar kind of formulas. Each time you get a bit tired. So you can look in other books, like Shimura's book, for instance. Ramanujan doesn't do this, but in Shimura's book, it's an action on cohomology also, group cohomology. Okay, so let's call this, write the title here, it's strange. Reinterpretation of Heck action on modular curves. Remember, modular curves are things like y1n or y not n or y of n, or just generally y of gamma. That's just h mod gamma. Okay, so yeah, I don't have enough space for the picture, so sorry for writing the title there. But here's the basic picture. So I want to let me write the things which are involved, not involved directly first at the top. Let's define y3, just using the same notation as before, h mod gamma 3. And remember, gamma 3 is notation alpha inverse gamma 1 alpha intersected with gamma 2. And y3 prime, let's define this as h mod gamma 3 prime, where gamma 3 prime, the denominator is what I'm defining here, is alpha conjugate, alpha gamma 3 alpha inverse, which is also gamma 1, gamma 1 intersected with alpha gamma 2 alpha inverse. And what is this map? This map is just multiplication by alpha. Tau goes to alpha tau. Equivalence class of that. So I'm not going to mentally check that that's well defined. You change something on the left by an element of that weird intersection, then the thing it maps to changes by an element of that intersection over there. All right, so we have y3 and y3 prime, but they're not really sort of the main objects of interest. We only really have a gamma 1 and a gamma 2. So more importantly, there are these maps to y2, which is h mod gamma 2. And similarly, there's a map here. These are surjections. There's a smaller congruent subgroup sitting in gamma 1. So you have a map to h mod gamma 1. Let's call this y1. Okay, so we have this following picture. All these spaces, all these groups and spaces fit into the following picture. So for be completely pedantic, I think in school we learned that, functions are the be all and end all of everything, right? The vertical line test. That you have a function and you draw a vertical line, it should intersect your graph exactly once, right? But as you get older, you learn that all these truths that you learned in life are wrong in different settings. Here, functions are not going to take 1 point to 1 point. They're going to take 1 point to many points. And maybe to distinguish that from the functions that we learned in school, we call these correspondences. Okay, so the Hicke operators can be thought of as correspondences. So what it's going to do is not map 1 point in y2 to 1 point in y1, but it's going to map it to many points in y1. And you can see how this diagram is going to be relevant without me writing any formulas. If you have a point in y2, you lift it here to a bunch of points, all the points which map to this point, right? The index of gamma 3 in gamma 2 is relevant there, right? Number of lifts will be relevant, but that's finite. We already discussed that. So there are finally many points that lift here. And you multiply them, each one of them by alpha. There's some taus there. You play each one of them by alpha. You get some tau primes, finite bunch of them. And then you push them down. They don't have to collapse to 1 point. Generally, they'll just be, if you lift them to d points here, push them across, there'll be d points, and you push them down, there'll be d points. So from beginning to end, you have 1 point mapping to d points. So this is what's called a correspondence. Okay, so let's write some definitions. So say gamma 1 alpha gamma 2 is the disjoint union of the representatives again, gamma 1 beta j. But let's do this intelligently. Remember, we can always pick our representatives of this form, alpha gamma 2 j, where gamma 2 mod gamma 3 by that lemma bijection in lemma 3, we had the following bijection. Let's write this as joint union. Gamma 2 mod gamma 3 is just a disjoint union of gamma 3 times gamma 2j, and you multiply on the left, right, by alpha, and you get representatives for this coset decomposition. So this is from lemma 2. So then, as I was saying, the square induces following operations, following mapping on points. So you'd start, I'll try and write this at the same height. So start with a tau down here. So I'll follow Diamond-Sherman's notation. They never take any shortcuts. So for example, they won't write tau there. They'll write the equivalence class of tau. So let's write it as gamma 2 tau. Then we lift that up to a bunch of points here. What are those points? We're going to get a set of points, gamma 3, gamma 2j, tau, right? One for each j. And we said that these coset representatives are finite. Okay. It may happen that sometimes you get the same points, so you have to do this with multiplicity. So if there's, I'm maybe going to fudge over this a little bit, but there's some ramification indices involved at some point. So you have to sort of repeat this point e times if e is the ramification index at this point. Okay, so that's in many of these formulas, you have to do that to make things correct. Right? But if the ramification index is always 1, then no issue like this. Okay, so with maybe I'll write it just once. Count it with multiplicities. For example, you may have just one point mapping to this point, and then some ramification, and you have to write that same point so many times. So count it with multiplicity equal to the ramification index. Right, then you multiply by alpha. So what does that go to? It goes to the bunch of these points, gamma 3 prime, alpha, gamma 2j, tau, which is the same as gamma 3 prime, beta j, tau by definition of beta j. We had taken the representatives beta j to be alpha gamma 2j. And then we push these down here to gamma 1, beta j, tau. This is a set. You start with one point and you wound up with a set of points. All right, so now we know what to do on one point. The double coset will take it to those points, but we want to sort of take finite linear combinations of points. You can see I'm being really primitive here. I mean, many of these things are already kind of done, right? Action on divisors, etc. Actions on Jacobians, they've sort of appeared in many of the lectures. So for those of you who are seeing it for the first time, like there was an I-star map in one of the talks on Jacobians just this morning. So I'm going to do those things a bit slowly. All of this is sort of here. Okay, so if divisor y is the divisor group of y, so finite sums of points in y with some integer coefficients in front, right? Finite formal sums. Formal sums with integer coefficients of points in y. Then just by extending things by linearity, you know what happens to one point? So you can just, what happens to a divisor? You get a map on the divisors from y2 to y1. So you know what happens to one point, so you know what happens to 2 points, etc., etc. Add normally. The plus signs everywhere. Okay, so now we have an action on divisors. Okay, so let us now begin to make things more number theoretic. This is sort of just some maybe topology or geometry or something, but into the number theory, we now are going to take alpha to be a particular kind of matrix. So this is probably the single most important definition of my 6 hours of lectures. The definition of the Heck operator TP. Okay, so TP operator is a prime. I'll write that. So what do? We specialize gamma 1 and gamma 2 both to, let's say, gamma 1n. It's a bit more complicated for gamma 1n. As you'll see, it's a little simpler for gamma naught n. I notice some of the speakers are assuming gamma naught n, but let me try and do as many things as possible with gamma 1n. Okay, so alpha equals 1p is your prime. Let me write it. Let's take specialized to this particular situation. Okay, so, well, we know what to do abstractly, right? We need to find some, decompose the double coset into single cosets, and then we just have to slash, right? Just move. So, okay, so how do you actually break this coset into single cosets? So let's try and compute some representatives. All right, so let's compute. So what is gamma 3? Gamma 3 is, by definition, alpha inverse, gamma 1, alpha intersected with gamma 2, but everything is simple now. They're all gamma 1n. Let me write this out a little bit. 1p, A, B, C, D, 1p intersected with gamma 1n, within gamma 1n. What is this matrix? This matrix is something like A, BP, C over P, D. Put that in your head. So it's the intersection of all these matrices intersected with gamma 1n. So you shouldn't be worried because this by definition is an integer, right? Because it's also in gamma 1n. Okay, so you're only looking at those things where C divided by P is actually an integer. And Lyman Sherman have a notation for this group. So they call this group gamma naught P. Upper gamma naught P, because there's a P with the B. So this is a completely different notation, which was not there so far. So this group gamma naught P is equal to set of all A prime, B prime, C prime, D, use slightly different notation, in SL2Z with B prime congruent to 0 mod P. Okay, so thought exercise to check that that is the most general element. Okay, so what's our guess? So let's try and guess. So we need to do some computations. Let's make a guess for the coset representatives and check that the guess actually works. So the guess is that the gamma 2j's that we choose for so how the coset the representatives you want to get are of the following kind. They're alpha times gamma 2j's, right? So first we need to find the gamma 2j's, and then we need to multiply by alpha. Those are going to be our beta j's. So let's first guess what the gamma 2j's are. Let's guess that. And what is this? Where is this guess coming from? Just to supposed to not be doing sort of just copying lots of formulas. So here you see that the B prime entry is congruent to 0 mod P, right? So you always get a multiple of P here. So maybe in the coset representatives, you want to take things which vary through all congruence classes mod P here. And that's going to be the guess. So we take gamma 2, 1 gamma 3 to be the following. Write this. Okay, let's write it like this. J is equal to 0, 1, P minus 1. And this almost works. In fact, it even works if P divides N was the level, P was the prime. But it doesn't work if P doesn't divide N. Explain why. So to tack on one more coset representative. Union, possibly a union here. You divide, does not divide N. You have to take one more coset representative, and that is the singleton set, one coset only. And the matrix is a bit complicated, but let me write it down. MP, little n, capital N1. Okay, so what is this? So the fact that P and N are, P doesn't divide N means N and P are co-prime. So therefore, you can choose M and N such that, let's see, I want to get the sign right, MP minus NN equals 1. Okay, so this is the matrix in SL2Z, and we take that particular matrix. This is one reason that people don't like to do gamma 1n. But anyway, I'm doing it now. Committed to it. A little simpler if you have gamma naught n. Okay, so this last coset here is only if P divides n. So this is not a guess anymore. That's with hindsight, of course. But the first part is an intelligent guess. So let's see why this is okay. The guess is okay. Just some ideas. Okay, so let's do some computations. So say gamma 2 is ABCD. It's in gamma 2. And okay, then what does it mean for gamma 2 to belong to, let's say, one of the first cosets? Gamma 3, let's call these names. Let me call this gamma 2J. Was the old notation over there. Let's call this gamma 2 infinity. Slightly new notation. So J is vary between 0 and P minus 1, and then gamma 2 infinity. So let's work with the first part. So suppose gamma 2 belongs to gamma 3 times gamma 2J. What does this mean? This happens if and only if we do a small computation, ABCD times the inverse of gamma 2J, which is 1 minus J 0, 1. Right? I just moved the matrix to this side. What is this computation? Let me multiply these matrices out. So this gives me A, B minus AJ, C, please check my work, D minus CJ. Belongs to gamma 3. Which we recall is now gamma naught P intersection, gamma upper naught P intersections with gamma 1n. Okay, so the question is, can you find a J such that gamma 3 is in that coset? And so what you really need, you need that this number should be 0 mod P. So we continue these equivalences if and only if B is congruent to AJ mod P, right? Because you want this to be 0 mod P. All the other conditions are more or less free because ABCD was in gamma 2, gamma 2, which was gamma 1n. So we already have that A and D are congruent to 1 mod n. Right? Those other conditions are fine. The only new thing is that we need B congruent to AJ mod P. And you can do this. You can solve this equation for a unique J if and only if P doesn't divide well. So take J equals BA inverse if P does not divide A. So as long as P doesn't divide A, you can actually solve this equation. There's no issue at all. Right? So you found a J and this is good. You managed to put one of these matrices into one of these cosets, the first few cosets here, all but the last, for some unique J, as long as your top left entry is not divisible by P. Okay, so something goes wrong when P divides A. Okay, so say P divides A now, what do you do? So note, first of all, that this only happens if P does not divide N, since we already know that AD minus BC is equal to 1. So if P divides A and P divides N, then there's a problem. C is a multiple of N. So P would divide C also, right? And that would be a contradiction because you cannot have the GCD being of D and B being 1. Would have a P in it, since there should be an else. There's a contradiction. Right, because C was 0 mod N, else means P divides N. Else P divides N, then C is a multiple of N, and then your problem. Okay, so we need to do something more, and this is why we need that extra coset representative. All right, so let's assume that P divides A. Okay, so say, I've already said that. Let gamma equals ABCD, gamma 2 maybe, or like calling it gamma 2. Gamma 2. Gamma 2 is ABCD with P dividing A. Okay, then similar computation as over there. Then gamma 2 belongs to, the claim is it belongs to gamma 3, gamma 2 infinity, if and only if, then computation. So you bring the gamma 2 infinity to this side. What's the inverse of that little complicated looking matrix over there? It's the following. You flip the A and D entries and multiply the B and C entries by -1. So you get a 1 here, an MP here, minus N, and a minus N here. And if you multiply this out, you get A minus BN minus NA plus B, C minus DN, please check my matrix multiplication, minus NC plus DMP. This should belong to gamma 3, which I remind you for the second time, gamma naught P intersected with gamma 1N. Right, this is what we have to check. Okay, so what are the conditions? Well, first of all, B better be 0 mod P, right? And this has to be 1 mod N, this has to be 1 mod N, and this has to be 0 mod N, right? That's the intersection of these conditions. So you can see that this is clearly 1 mod N. Mod N, the N goes away. A was already, A and D were already coming to 1 mod N. What about this? C was already 0 mod N, and this is already 0 mod N, so this is 0 mod N. That's also a check. I think I made a mistake in multiplying my matrices. Nobody's saying anything. Minus NA plus BMP. Thank you. Yes. So we have to check that that is 0 mod P. So why is that? Well, this goes away, and P divided A, right? This is also great. 0 mod P and P divides A, that's where we use the condition. And finally, the last one is this had better be 1 mod N. So, why is that true? Well, C is 0 mod n, so that's not there. And what about this? D was 1 mod n. Don't see it. I'm standing at the blackboard and not seeing it. Yes, yes, go ahead. It should be 1 mod n. Yeah. MP is equal to 1 plus, great, thank you. MP is equal to 1 plus NN, correct, great. And so this is just D mod n, which is 1 mod n, and that's 0 mod n, right? Just making that substitution, get that. Okay, so all of these are checks. And we've checked that just by adding this one coset, you wind up these coset represents seem to work. Maybe I'll continue over here. All right, great. So putting all this together, we get, let me just sort of rewrite this. Gamma 1 mod gamma 1 alpha gamma 2 equals gamma 1. Okay, so we found the coset representatives for gamma 2 mod gamma 3, and that's the little gamma 2j's and gamma 2 infinity also. But now we want to multiply on the left by alpha to get the coset representatives of the double coset. To break this double coset into single cosets, we just multiply by alpha on the left. Okay, so this was by definition beta j. And explicitly, what is this? This is 1p. Now it's beginning to look familiar to you. If you're an expert in the subject, you'll see that this is exactly right. You get 1j0p. Okay, so that's the first bunch. And then for the last one, union, there's the singleton coset here, singleton set with one coset, beta infinity. Let me write it as alpha gamma 2 infinity. This one, let's call this beta infinity. This is the definition. Make these choices. Going by alpha, the representatives. And what is this computation? So let's do this 100p times this slightly strange matrix mpn. N capital 1. Okay, let's multiply things out. Maybe I'll use my notes and you can just check, make some mistakes otherwise. MPN, EN, E. And this can be written as MN0P times E001. Sorry, MNNP. So the matrix actually became slightly clean at the end. First, the ones with MNNs, little m's and little n's showed up here at the end. Okay, so this is the sort of, we've now actually found explicit coset representatives. So putting everything together, get the proposition that if n is greater than or equal to 1, then the TP operator, which is gamma 1n 1p, gamma 1n, it takes nk gamma 1n to nk gamma 1n. It's given by the slashing by the beta j's. And we just found the beta j's explicitly. So let's write the formula down. EP of f is equal to the sum from j is equal to 0 to p minus 1 of F/1J0P, right? We just slash by the coset representatives, plus possibly another term. This term is only there if P does not divide N, F/2 matrices, M, N, NP, and P001. Okay, so this is the explicit formula for the Heck operator, done according to Diamond-Sherman. Okay, so there are various other motivations for this which are not in the book. Maybe I'll say something. So one of the questions that you sometimes get when you're taking an interview, at least at TFR, is how many index 2 subgroups are there of Z cross Z? Right, so everyone says 2Z cross Z and Z cross 2Z, but they forget the third one. Right, there's a diagonal one, all XY, where either both X and Y are even or X and Y are odd. And that's also a subgroup of index 2. It's the preimage of 1, 1 under a map from Z cross Z to Z mod 2 cross Z mod 2, which preimage of the element 1, 1, right? That's also an element of order 2. So that shows you that there are 3 subgroups of index 2 inside Z plus Z. And that 3 is P plus 1 for P equals 2. And so these representatives are basically measuring the number of subgroups inside Z squared of index P. Okay, there are P plus 1 of them. So if you want to go further back, you can go to the Brouhatitz tree, which is a graph. So mathematics gets simpler and simpler and can be abstracted. So there's a picture where the lattices inside Z2 or QP squared are just given by dots. And then you connect 2 lattices by an edge in the graph if there's an index P containment, roughly. It's actually lattices up to homothety. So you have to check that this is well defined. But this graph therefore has valency P plus 1. And there's a canonical operator on this graph, which is the sum of neighbors operator. If you have a function on the tree, the value at a point, you can just apply all the values of all the neighbors, right? Canonical operator in graph theory. So anyway, there are many avatars of the Heck operator. If this looks very computational, there are various motivations for this. For example, if you look in Serre's book on arithmetic of, what is it called? Small book of Serre. Sorry, course in arithmetic. Course in arithmetic, yeah. So at the last chapter, I think he does some this lattice interpretation, but maybe not the tree interpretation. Okay. So this is the formula for the Heck operator. All right, so you can make this even more precise, and that's the formulas in many books and Diamond Im. So now you can ask what happens on Q expansions. I won't write that formula down. It's just a formula that's in every book, and people just often define that to be the TP action or TN action. I haven't defined how TN acts, but I'll say a few words. Okay, where are all the erasers? Any questions while I'm erasing? Okay, so the next thing we want to do is give a modular curve interpretation of the Heck operator. Modular interpretation of TP. So if you take these particular representatives, just wrote them down. We had defined 2 actions of Heck operators, at least of TP. Now we have the representatives, we can define the action on modular forms, which I did over there. And you can also define the action on as a correspondence on modular curves. And at the end of last lecture, I gave a moduli interpretation of the points of the modular curve. So what is the moduli interpretation of TP now? Okay, so the claim is that moduli interpretation of TP, the claim is that let's work with gamma 1 n. General thing. Well, I should have made this remark, which I forgot to make, that if you work with gamma naught n, that ugly matrix goes away. Do people see that? Why is that? It's not there in many books, right? But it's there on the blackboard. Little m, little n, capital NP. That goes away because if you're in gamma naught n, that matrix is in gamma naught n, right? The lower left entry. The determinant is 1 by hypothesis. Lower left entry is divisible by 0, right? And the slashing by that is invariant. So it goes away. So you can actually drop that matrix. And then that's mostly the formula that's there. A bit simpler. Okay, so all right, let's talk about the modular interpretation of TP. So we know what it does in general, the double coset operator. So what does it do specifically to these, what did I call them? Enhanced elliptic curves. What does it do to them? So the claim is that this is elliptic curves, isomorphism classes of elliptic curves, like using lecture 1. EQ is going to, so you can write it very cleanly without much notation. So it's the following formal sum. So it's, you take all subgroups of index P in E, sorry, of cardinality P, with the property that C intersected with the subgroup generated by Q is the 0 subgroup. And you look at E mod C, and although I'm in Sherman's notation of writing points like this, as cosets, they don't cheat at all anywhere, the notation. So write Q plus C instead of just Q. The image of Q in E mod C. So this is sort of a very beautiful formula. It's telling you how the Heck operator acts on elliptic curve in a point of order n. There's a whole bunch of other, how many? Roughly P plus 1, right? P or P plus 1, depending on various things. But so we have to check that also, that these conditions are either giving P subgroups or P plus 1 subgroups, depending on the two cases. But you have some elliptic curves and some points of order n. Okay. This is the last thing I think I want to check today. Do this. Proof. Before I make some general remarks, and the last formal thing I want to prove. All right, so what is TP doing? It's acting on divisors. Let's recall that formula. We had gamma 1 n tau going to a formal sum with coefficient 1, gamma 1 n theta j tau, right? I'm including j equals infinity in there. Including j equals infinity when it does not divide n. Okay, so this was the general formula for any modular curve. Let's specialize it now to number theory setting with TP, etc. So I've already done that for gamma 1n, but let's make this more explicit. So, so first of all, by lecture 1, we can write EQ as this was the first part of the second part of that theorem. End of the lecture, as E tau, so C modulo. You can always pick a representative of this kind, right? We're working with, by the way, elliptic curves of the complex numbers everywhere here. Every EQ has a representative of the form C modulo the lattice span by tau and 1, right? And the point of order n can be chosen to be 1 over n, right? 1 over n plus lambda tau. You can always choose the isomorphism class like this. Okay, so therefore, this was corresponding to the point gamma 1 n tau, here perhaps y1 n. Similarly, beta j tau. Therefore, okay, let me flip the order. This corresponds to C mod lambda beta j tau, and then 1 over n plus lambda beta j tau. So we need to understand this. Okay, so let's do two cases. Let's try and understand this particular isomorphism class of this particular pair here. So suppose j is not equal to infinity. Okay, so in this case, what is lambda beta j tau? Explicitly, it's just z. So beta j was 1j 0p, so make that act on tau, you get tau plus j over p, sorry, z times this, plus another z times 1. And this contains lambda tau, right? Because both the generators 1 and tau are in that lattice, right? Any guesses for what this index is? This is related to what I was just talking about. It's the two free subgroups of rank 2. The index is finite. Any guesses? Index is p. So you can think about this. If you multiply this by p, it goes in there. Okay. So let's rewrite this object using this fact here. So let's write C mod beta j tau, sorry, lambda beta j tau as, this is the main trick. You write it as C mod lambda tau modulo third isomorphism theorem, lambda beta j tau mod lambda tau. Right? I'm writing all the steps here. Cyclic subgroup generated by tau plus j e plus lambda tau. And so this is the format e tau modulo cj. Right? This is a subgroup of index p, this quotient subgroup. Right? Let's call that cj, that subgroup. So it's just a question of using the third isomorphism theorem, rewriting things. So at least for the elliptic curve part, we managed to recognize this as E mod C for some C, right? It's in this format. What about for the other coordinate, second coordinate here, second element of that pair? So one observation, the second one is similar. So 1 over n plus beta j tau, what does this correspond to? This is the point Q. Right, in this third isomorphism theorem, if you want to write 1 over n, the correct notation, you write it this way. Let's check things. All right, so we have managed to show that this is the case j not equal to infinity is just E mod Cj mod Q plus Cj. Okay, what about the other case? What if j is equal to infinity? This one's a little trickier, so let's do it. So lambda beta infinity tau. What is this? So this is z. So we computed beta infinity tau. Did I erase it? I shouldn't have erased it. I think I erased it, but I have it here in my notes. So it was MP N NP P acting on tau. This was beta infinity. Plus Z. Beta infinity. Just go look back. Okay, and so let's expand that a little bit. So this is MP tau plus N over NP tau plus E. And plus Z. Sorry, I should skip some of these steps. Let's divide by P. We get M tau plus N over P. N tau plus 1 plus Z. Okay, so let's rewrite it in this way. This is the lattice lambda beta infinity tau. All right, therefore, let's clear denominators. So this is going to be the alpha in previous lectures. Let's if you multiply by alpha, this is a non-zero number, tau cannot be minus 1 over n. That was in the upper half plane. So multiplication by this alpha on lambda beta infinity tau gives, it clears denominators, and you just get Z m tau plus n over p plus Z n tau plus 1. And we can simplify this because the GCD of M and N, remember there was some relation, write it again, MP minus NN equals 1, using this all the time. Forgot to use it one time last time. Using that here, Z, M and N here, they just give a Z tau. And over here, you get a Z 1 over P. So the trick is to write this 1 as P over P. And it's easier to see. N and P, the GCD of N and P is 1. Right, so write that 1 is P over P, and then you get a Z 1 over P. Okay, so what does all this say? Oh, it was over here. See it over here. This is one remark. The second remark is that, what about if you multiply n tau plus 1 on, okay, maybe I don't need that. Yeah, I don't think I need that. Okay, so let's look at C mod lambda beta infinity tau. So we're multiplying by n tau plus 1. And we just said that the numerator, of course, goes to the numerator, but the denominator we just computed went to some lattice of this form, Z tau plus Z 1 over P. Which now by the third isomorphism theorem, let's write as C mod lambda tau modulo this group, Z tau plus Z 1 over P modulo lambda tau. Right, and this again now is of the form E tau modulo, let's call it C infinity this time. And what about the 0.1 over n plus beta infinity tau? Sorry, lambda beta infinity tau. What does this correspond to under the third isomorphism theorem? It corresponds to 1 plus lambda tau. Write something here, modulo the denominator. This is your cube. That's the other case over here. Infinity is just E. I'm just talking about the first, this term here. So E C infinity modulo Q plus C infinity. Okay, so we're almost done with the moduli interpretation. So putting all of this together, we now see that we have P or P plus 1 subgroups of E. Let me not erase this formula, maybe. Let's erase this. The claim is that these are exactly the subgroups of index P. Another interpretation of the Heck operator. Equivalent to the one with lattices, you're just looking at quotients rather than subs. Right, these are the subgroups of index P inside Z plus Z. The direct sum Z. So note collection of the CJs. J is equal to 0 to P minus 1. Union C infinity are exactly the subgroups of order P in E. So how do you check this? There's some numerical check. They're all disjoint. For example, I think the last one, yeah, they're all disjoint. Okay, so let me not try and check that on the board. Yeah, so a small check that they're all disjoint. Let's leave that. So check all disjoint. Disjoint in the sense the intersection of any two is 0. Intersection of any two equals 0. No repetitions. Trivial check. And the union, therefore, was the cardinality of their union, including J equals infinity here. So how many of them are there? There are P plus 1 and P minus 1 elements of order P. If you drop 0, then you have to include 0. That gives you each of these has to be sitting in the P torsion. Any subgroup of order P sitting in the P torsion, and this is filling out the P torsion, right? Filling out the P torsion, so there are no others. Any other subgroup will be forced to be on the right and therefore have to be in the left. One of these. Okay, so that's good. Now, what about this subtle thing of dropping one of the representatives? So let's do a small check here. Moreover, claiming that the Cj intersects 1 over n plus lambda tau, was the subgroup generated by Q. It's mostly 0. So if in the finite J's, it's always 0, right? Because the finite J's had a tau plus J over P. Tau is a complex number, so it has some complex thing in it, whereas this has a real thing, 1 over n, right? Going off in different directions in that parallelogram. What about at J equals infinity? I'm claiming it's still 0 if P does not divide n, and not 0, unfortunately, or fortunately, if you want the formula to work, J equals infinity and P divides n. Right? So here we have a 1 over n in Q, but what was it for C infinity? It was a 1 over P. Right? So multiples of a half and 1/3, they won't meet each other. Right? If P and N are co-prime, then they'll never meet each other. So the intersection will be 0. But if P divides N, then multiples of a half and a 4, 1/4, they'll meet each other, right? The intersection will not be 0. Okay, so only in the case where P divides N, you have to drop C infinity. So this condition here that C intersection Q is equal to 0 is a fancy way of saying let's drop C infinity when P divides N. Okay, so that's the modular interpretation of the Hecke operator TP. I was trying to focus as much as on modular curves as on modular forms, because it's supposed to be a course on modular curves. Where am I? Some things. Okay, so no more proofs. I'll just speak for about 10 minutes on where to go from here. Okay, so this was the end of the proof of the claim. 15 minutes ago. It's still up there. There's claim somewhere? Yeah. Okay. So now let's move to Tn. We've defined Tp for every prime P, both for P dividing N and for P not dividing N. All right, so now I'm going to have to start hand waving because this is another 1 month course in modular forms. So I can't write all the formulas down, but this stuff is fairly standard. And so let me just make some remarks. So Can defines, instead of Tp, you can define Tn now for each n equals 1, 2, right? So well, you make T1 just 1, and you make T prime power to be given by this formula. Okay, I need this diamond operator, which I haven't defined, but not so serious. I think this book by Fred Diamond, he gives equal weightage to the diamond operator. I wonder why. Probably because he have the same name, but 50% of the book is about the diamond operator and the modular interpretation of the diamond operator, and the diamond operator is everywhere. I hope I'm not being recorded. But yeah, it's not really an important operator. Anyway, it doesn't do anything too fancy. Okay, let me not even try to define it. So I decided to ignore it completely, but okay, you need it here. This, just say diamond operator. There's also a diamond operator and a modular interpretation of it, etc. Some people call it the TPP operator. I think Shimura will be called the TPP operator, up to some scalar maybe. So, okay, there's another kind of Hecke operator, one with 2 indices instead of 1. Okay, so Tn is then the product of these TPRs, where n is equal to product of P to the Ri. Write the prime factorization of n down and then just multiply all those operators together. So this is how Tn works. So, okay, so you get Hecke operators for every natural number. Some more facts. So there's a Peterson inner product, which I won't even, what's the spelling of this? I hope number of S's and T's are correct. Inner product. You can pair together 2 cusp forms, or a cusp form and a modular form with some integral, basically multiply the forms together. Take the conjugate of 1 and integrate over on H mod gamma, some Haar measure, some invariant measure, which you have to integrate against. Okay, so there's this Peterson inner product on Sk gamma 1n. And these operators, Tn, at least for n co-prime to n, are self-adjoint. Self-adjoint with respect to Peterson inner product. Okay, so therefore you have a basis of eigenforms for these particular operators. Basis of common eigenforms. A commuting family of operators is commutative situation and basis of eigenforms. Yes. Oh, yes. Okay. Yeah. Yes. Okay. Yeah, this part I didn't really prepare. I just made some notes. You're saying there might be some, yeah, because yeah, Tn star should be something like epsilon n inverse times Tn. So there'll be some diamond. So An bar, the complex conjugate An bar of the Fourier coefficient is given by An times epsilon n inverse. You're right. If there's an even typist, one has to maybe be a bit more careful. Okay, so my comment came back to bite me on diamond operators. All right, so maybe they're more important than I thought. Yeah, so okay, so I'm maybe listing some facts here. So anyway, you have a basis of eigenforms. Warning, you do not get a basis of eigenforms for all the Hecke operators, just for the Tn's, coprime to n, but there's a nice subspace called the new subspace, which are basically modular forms which don't come from smaller level. And on that, you actually get a basis of eigenforms. I won't write that. Okay, what else do I want to say? So, okay, maybe I'll write that. On Sk nu, gamma naught n, let's be a bit careful. Maybe there's some issues with gamma 1. I haven't thought about carefully. On Sk gamma naught n, there's a basis of eigenforms. Nu, I won't try and define, but it has something to do with the Pearson product. So nu means that any modular form of level 1 is also modular form of level 10. So it's a fake modular form of level 10. So you somehow think of, you take the orthogonal complement of all these kinds of forms under the Pearson product. That's the new space. A bit more than that. You have to also look at f of 2z and f of 5z and f of 10z. But anyway, you look at the space spanned by such things and you take the orthogonal complement of that. So you get this new space, and over here you have a basis of eigenforms. Okay, so let's forget about this for a second. So start with a eigenform. I wanted to really say something about integral structures. I'm trying to be complete in my course here, which is almost impossible. Let's try. So say f is an eigenform normalized with a1 equals 1. Then the eigenvalues, I'm not going to write all the notation. Let lambda n be the eigenvalue for the nth. This eigenform now is a common eigenform of all the Hecke operators. Forget the new old stuff. You might have some old forms which are also eigenforms called the Hecke operators. So take an eigenform. It turns out that the lambda n's, the eigenvalues for the nth operator, are equal to an. Okay, so that's one nice thing. You can recover Fourier coefficients from eigenvalues of Hecke operators. I'm trying to get to the statement that the ANs can be taken to be algebraic integers. Maybe one thing. One of the speakers wanted the following statement, so let me just say it without proof. I'll come back to the integral structure in a second. So let T be the Hecke algebra. So here I mean the subalgebra generated by the Tn's inside Sk gamma 1n or Sk gamma naught n. Sk gamma naught n for simplicity, but maybe gamma 1n after gamma 1n. So I think the following statement was requested. So let me just write it. There exists a pairing between Sk gamma 1 n. Maybe there should be Tk gamma 1 n or something. That's T cross C, which takes F and the Heck operator T. So this is generated by the Heck operators. It's a subalgebra of Sk gamma 1 over complex numbers generated by the Heck algebras. And you just take this to A1, the first Fourier coefficient of T of F. So these are vector spaces, and you have a pairing between these vector spaces. This turns out to be a perfect pairing. There's some notes on these kinds of things from old courses I've given, but they're in many places. This is a perfect pairing. So the dimension of Sk gamma, of T is equal to the dimension of Sk gamma 1 n. Okay, so even though it's a subalgebra of the matrix algebra, which is dimension n squared, if n is the dimension of Sk, it's just n dimension. Okay, so coming back to this integrality issue. So so this is the goal of the course in some sense. Run out of time, but let me just write a few more remarks. We want n's to belong to Z bar, them to be algebraic integers. Okay, so now I'm going to just make some loose remarks. So what we need is a Z structure on Sk gamma 1 n. So suppose we can pick a basis of Sk gamma 1 n where the Fourier coefficients are all defined over Z. And one can easily check by that formula that I gave, that on Q expansions you get some explicit formula. That formula actually preserves modular forms whose Q expansions are defined over Z. Okay, so that's clear just from the formulas. But what's not clear is that there is actually a basis like this, that you can actually find modular forms defined over Z whose C span gives you the whole space. So this is a very tricky thing to do. Yeah. So there's several different proofs of this, and I was planning to give one or two in this course, one next time and one in the fourth lecture. So before I say those fancier proofs, let me say this: the silly proof is you just try and write it down. Okay, so proofs, explicit computations. Let me say something explicit basis. So this is what I referred to last time. For example, in level 1, you can take multiples of E4, E6, and delta with the appropriate powers, such that 4a plus 6b plus 12c is equal to the weight, right? If you take all monomials like this in those three things, it turns out to be a basis of Gus forms. I hope I'm saying this more or less right. I just realized that maybe C is 0, then you don't get a Gus form. But okay. But roughly that's right. And it turns out that the Heck operators preserve that space. And so that will give you, at least in level 1, some sort of explicit basis. And you can try and do this for level 1, 2, 3, etc. But then, of course, you'll run out of ideas at some point. It's tricky. So the second proof, which is in Shimura's book, and the one that I mostly know, is that there's an isomorphism, Sk gamma 1 n, to H1 parabolic gamma, same k minus 2, r squared. An isomorphism of real vector spaces. Complex vector space on the left, think of it as a real vector space. Okay, let me not define all the notation. This is a subgroup of GL2, so it acts on column vectors and therefore on symmetric powers of column vectors, right? This is just group cohomology, and this is parabolic group cohomology. You're looking at cocycles which when you restrict to stabilizers of cusps, they basically vanish. It's the kernel of the map from full H1 to H1 of the boundary of the Borel-Serre compactification, if you've seen that. So how is this? Looks much more complicated. How is this useful? Well, it's very tricky to write down a basis here over Z, right? But here it's trivial because you can look at sim k minus 2 Z squared, right? There's an integral structure here which is trivial. And if you look at the formulas for the Heck operators on group cohomology, which I haven't had time to define today and will not define, it turns out they preserved the integral cocycles. So that Z structure shows you that the Heck operators actually have entries with coefficients in Z. By the way, this is a Heck equivariant isomorph, so I'm not defining it, but it's basically given by some integration. Very standard thing. So that's the second proof. And the third proof is using Jacobians. Yeah, so let me just say, let me write not too much because I want to do this in detail next time. Let me just write this. Use the first homology group of Z. So what we'll do next time is to show that the Heck operators, which we defined today on modular curves, they induce an action on Jacobians. Jacobians are quotient of two things. There's already action on the top. And you also now have an action on the quotient, and therefore you have an action on the denominator, and the denominator is exactly the homology, first homology. So you get an action of Heck operators on the first homology group. That is the proof that Diamond gives, and that's more or less of the same flavor as the one with the Eknath isomorphism. That's the third proof. And the fourth proof, which I was also requested to do, is one using the Q expansion principle. I'll do that in the fourth lecture. This is lecture 3. This is lecture 4. Okay. Yes. That's true. That's true. It only works in weight 2. That's true. This Eichler-Shimura proof, yes, it works in all weights. But if you take the trivial coefficient system, it's kind of equivalent to that proof. Yeah, that's true. That's a good point. I wonder if Diamond Sherman does it in arbitrary weight. I didn't check very carefully.
Any more questions?
Got product from, so there is actually, so this, we should think of this as the Ram cohomology and this as Betty cohomology of some space. And there are various pairings. I don't know whether they're the Peterson product. They must be essentially equivalent to the Peterson product. You can pair two differential forms and multiply them and integrate them. So what I want to say is that just from general topological things, you have a pairing between H1 of a curve and H1 compactly supported of a curve to complex numbers just by taking two differential forms, integrate and then wedging them and integrating them, right? You get a two-form integrate over the whole curve. That's Poincare duality or something. That basically is the Peterson product when you integrate. Basically get the same formula. That pairing is used quite a bit. You want to prove rationality results for L functions and things.
Any more questions? Let's thank the speaker again.